This first lecture of this workshop or seminar in experimental aeroacoustics will be introduction to plane wave decomposition and two-port analysis in flow duct acoustics. So it will have a short introduction and then something about so-called one-port measurements, the two microphone techniques, and something about sources of error, and then two-port measurements and something about to handle flow noise problems that you might get. Okay, so this slide just shows the wave equation, which I hope that you recognize. And here we are looking at sound propagation in ducts. And in this case, we are beginning today with low frequencies, that is only plane waves, so only one mode is propagating down the duct. And then you could have mean flow denoted by U here in the slide, and then you get a modified wave equation including a term where the flow's velocity is included. And the solution to this equation for one-dimensional plane waves for the pressure will look like this. So there's an amplitude P hat, and there's a propagation term e to I kx times x, so k being the wave number, kx times x the Helmholtz number, and then there's a time dependence term which we will immediately throw away because that will appear everywhere, and we will remove it. Maybe there's a problem with the sign here in this equation, because probably there should be different signs in the kx and I omega if there's propagation in the positive x direction. Anyway, this wave number, if you have mean flow, it turns out that you can modify it using the Mach number m, because basically the sound propagates faster with the flow and slower against the flow. So you get these two wave numbers in the positive and negative flow direction, which in this case is also the same as the x direction. So the total pressure field which we will use looks like this. So it's the amplitude of the wave propagating in the positive direction times the propagation term with the kx plus wave number, and then there's the amplitude of the wave propagating in the negative direction times another propagation term.
Hans, are you trying to use the pointer?
Not at the moment.
Okay,
I guess you can't see it. But,
no, exactly.
So I don't know exactly how to do it.
But now, what you did now, you could see. So this is fine.
Yeah. So now it's okay. You can see the pointer.
Yep.
Yes, I will use it later on. Okay, and then the plane wave range only exists up to a certain frequency, and then there will be propagation of higher order modes. So this table just shows when they start to cut on, as we say. So for a rectangular duct, it will be when there is half a wavelength across the longest direction, and for the circular cross-section duct, it will be slightly different, but not so far from this. And tomorrow morning, my colleague Mats will give a talk about measurements for higher order modes. But today we will concentrate on the low frequencies plane waves. Okay, I always show this photo when I talk about these kind of things. So this is a picture from the mid-80s. So this one over here, that's me, and that is Mats. And it's sort of when we started out with in this field of doing measurements for duct acoustics or so. This little box here was the first PC in the lab. And the big box behind is the data acquisition front end for the LMS system that we just bought. So since this was the first PC in the lab, I usually ask people to think about also, what did you actually do when you did research or worked at university before you had personal computers? Well, you did something, but maybe it's difficult to imagine, because nowadays, I guess, people spend a very large percentage of their time sitting at their laptop. Yeah, this is just a picture of a setup from that time. It was some measurements on parts of an intake system for a car. You see 2 microphones mounted here, the duct. And this is a more recent picture. It's not very new, but it could look like this today also. So this is from our flow test rig, which we have at our lab at KTH. So there will, in this case, there will be flow coming down this duct, and these big things here, they are loudspeakers. And then there are some microphones mounted over here. You can see 1, 2, 3 here at least, and some more over here. And typically there will be a sample of some kind sitting here in the middle. Yeah, so as I said, me and Mats, we started out with this. So we started out doing these measurements, and then we found some strange results. So we started thinking about errors that could occur. So we have a few papers from at the end of the 80s. This one is from 86 and this one is from 88, about the influence of errors on these kind of so-called 2 microphone measurements. Yeah, so the idea of the 2 microphone technique is actually quite simple. So it looks like this. You have a duct, you have a plane waves propagating in the positive and negative direction. And you could also have a mean flow indicated by this arrow here and M for the Mach number. And there's a distance between the microphone. It's called S in this case. And of course you could have more than 2, but it turns out that 2 is in principle enough to do what this so-called wave decomposition, which is the purpose of the 2 microphone method. Before this, the 2 microphone methods, it was common to do similar things, but you had a setup where you had a microphone that could be moved along the duct to different positions. But in the 1970s, this technique, 2 microphone technique, was published and became popular, or beginning of the 80s. And the reason why it became popular at that time was that also the development of computers and measurement systems, which made it possible to do Fourier transforms or so easily from time series. And this is, of course, the thing, or this is the thing that you will try to do later today. So the basic idea of the 2 microphone is quite simple. So you remember we have this equation for the pressure field. So you measure at 2 positions, at this P1, we put x equal to 0 here, so these complex exponentials disappear, and that P2 is distance s from the position where we measure P1. So you have these two equations, and the thing that you are looking for is the amplitudes of the waves, the P plus and P minus. And if we would know these complex exponentials, then we simply have a system with linear system with two equations and two unknowns. So we can solve the equations and get the unknowns. That's the basic idea. And to know these complex exponentials, we need to know the wave number. So it's the frequency. We need to know the speed of sound. And with flow, we also need to know the Mach number. And then we need to know the distance between the microphones. So in principle, we could measure or determine these things in separate ways, separate from this measurement. So we would know them, at least as a first idea. And then we can solve for P plus and P minus until, for instance, calculate the so-called reflection coefficients, which is P minus divided by P plus. So it's the ratio between the reflected and the incident wave amplitudes. And maybe you notice that the notation is not completely consistent because we have hats on these P plus and P minuses before, but they have disappeared here. But anyway, it turns out that this then reflection coefficient can be determined from this by solving the equations. So we see what we want is the ratio between the two pressures, P2 divided by P1. And then we need still to know this, the complex exponentials here. And P2 divided by P1, that can also be expressed as a frequency response function with 1 as the input and 2 as the output. Yeah, and that one we could sometimes denote by H, so H1, 2. In this case, so then the reflection coefficient can be written like this. And this is the reflection coefficient now at the position of microphone 1. So it could also be moved to x equal to L, that is the place where we have the sample. By this equation. So typically we would like to know the reflection coefficient at a specific cross-section where the sample, whatever that is, starts. And then we can also calculate the normalized impedance, which is defined as the pressure, acoustic pressure divided by the particle velocity u and normalized by the density and speed of sound, which is the impedance of a propagating wave, freely propagating wave. And it can also be written as 1 plus the reflection coefficient divided by 1 minus the reflection coefficient, such that when the reflection coefficient is 1, meaning that it's total reflection, such as a hard wall, then the impedance is infinite. So hard wall would mean infinite impedance. If the reflection coefficient is equal to -1, which for low frequency is close to what you have for an open end, then the impedance is 0. And if there's no reflection, so the reflection coefficient is 0, then the impedance is 1. as I said, that's the what you get for a freely propagating wave in one direction. Okay, so that's basically it, and those are the things that you will do or try to do later on using some data. So now I will say something about also errors that you could get. So we have this quite simple equation, for instance, for the reflection coefficient, and then we found that there will be errors in this. There is always some errors in when you do experiments, because you can never do a perfect experiments. You can try your best to do it as good as possible. But how can then these errors enter into this equation? Well, they must come in through the input data that you put in. So it's basically the so-called Helmholtz number, k plus or k minus times s, or into this frequency response function or pressure measurements. That's the only way that you can get them. And you can have some uncertainty in the termination of the wave number. If you have flow, there might be uncertainty in the losses, turbulent losses, for instance. There's also, of course, the speed of sound, which is included, and as you know, hopefully that depends on the temperature. So you need to also have a temperature measurement and keep control of the temperature to know this accurately. And that also enters then into the Mach number, where we have two parts: is the speed of sound, and also, of course, how to determine the flow speed. So you need to have transducers. We often use Pitot tube to determine the flow speed profile, because the flow profile will not be completely flat in a duct. And then it's the distance between the microphones, so of course there will be some uncertainty in this measurement. So it says geometric and acoustic length. So geometric would be, you take a ruler and you measure it, and you can only do it down to a certain accuracy. And then the acoustic length has to do with the fact that you can never do a measurement without creating some kind of disturbance. So the fact that you put microphones in the duct will have some influence on the sound field. So that could influence some kind of equivalent acoustic distance between the transducers. And then it's the errors in the measured pressures. So there will be so-called systematic or bias errors. There's something called resolution bias that could occur, which gets worse if you have a long duct with many resonances, many peaks. So it's good, so it reduces the reflections in the duct to have less variation in the spectrum at the microphones. And then there will be random errors caused by maybe random singlets, but mainly due to flow noise disturbances. So there will be turbulent flow in the duct, and this creates turbulent pressure fluctuations, which will be picked up by the microphones. And we only want to pick up the acoustic pressure variations. So there was a need to develop techniques to get rid of these so-called flow noise disturbances. Yeah, so this is an example what the spectrum could look like at one microphone. So in this case, we have frequency on the x-axis, and on the y-axis it says pressure out of spectral density, dB. Well, basically it's the pressure in dB Okay. I don't know if it's actual dB, which is relative to the correct reference. But anyway, it's in dB, so it's a relative measure between the. So you see there's like a 50 dB difference between the lowest and the highest values. And these red ones with the peaks, that's the risk for regions with risk for this resolution bias problem, which could be improved if you improve the frequency resolution. Because the problem is if you have very narrow peaks and you're not able to resolve them, that creates a bias error problem. And regions where you have very low levels at the microphones, because if you have reflections in the ducts, you will have cancellation of the waves going in the positive and negative direction at certain frequencies at certain positions. And then if basically the pressure goes to zero, then background noise will be of higher importance, like this flow noise disturbance or other background noise. And then there's a bigger risk than in these places to have. And of course, if you move to another microphone position, these will move to other frequencies. Some of them at least, these minimas, for instance. And then in these two papers that Mats and I produced, we came up with this equation, which we use for how to avoid large errors. So the upper one is actually also if the Helmholtz number k times x goes to pi, or pi times 1 minus the Mach number squared, then the whole method breaks down, because it's like if you have a wave and you move along, you move half a wavelength, then you sort of get back to the same equation. If you remember, we have this system with two equations, and you need to have two independent equations in order to solve this system. So if we move so that these two equations are no longer independent, then the whole thing will break down, and also close to this, the error becomes very large. So in the upper range, there's a safety margin of 0.8 instead of 1. And then you should also avoid a very low frequency region because it's more difficult to you get larger errors due to the phase measurements between the two microphones at very low frequencies. Yeah. So this, if you choose a certain distance between the microphones, this then limits the frequency range, which is useful. And if you want to extend the frequency range, then the solution is to have more microphones. So you very often we have at least have 3 microphones, so a short distance or a bit longer distance, which are measured at the same time, and then you can cover a wider frequency range. Yeah, okay. Calibration. For these kind of measurements, you need to do something called relative calibration. And you will have to do this in this task you will work on in the afternoon. You will get the calibration file, which is measured in a way similar to this. So in principle, it's like this. You have a loudspeaker in a duct. You stay in the plane wave range, and you put your microphones at the end of the duct so that they are exposed to the same sound field, and then you measure the relative amplitude and phase between these two. So they should have the same amplitude and no phase difference, basically. And if you take the frequency response function dividing B by A, then that should be equal to 1. So the amplitude is the same, the phase is 0. So any deviation from that is caused by some calibration error in your system, in the microphones, in any signal conditioning that you use, or in your analyzer system or data acquisition system. In principle, it's like this. Very often, in our case, it looks like in the photo. So you have a loudspeaker here, you have a short duct, and then you can mount a number of microphones around here, and then you have some plug here at the end of this duct, making sure that you have a hard termination very close to where you put the microphones. And the point of putting the microphones close to this hard termination is that there you have a maximum of the pressure, because you have total reflection, so you have a pressure maximum there, and you get a good signal. Okay. Yes, so then I would say something about overdetermination. I already mentioned that you can introduce more microphones to have a wider frequency range, but you can also do it for other reasons. So one possibility is that you add more microphones, you get more equations, you get an overdetermined system, which could basically be used to reduce error in the measurements. And this was, for instance, studied in this paper by one of our PhD students at KTH, now almost 10 years ago. You can also add more microphones for other reasons. You can do it to solve a nonlinear system of equations. So you no longer assume that you know these Helmholtz numbers, the K plus S and K minus S. You keep them also as unknowns. And then you need more information to solve for this. But unfortunately, it's no longer a linear system of equations, because you want to solve for these things which are in the complex exponentials. But that has been done also by some of my colleagues at KTH. So there's this paper from 2006 about this. Okay, so I think that was the part about one port which I wanted to talk about now. I will, in my talk tomorrow, I will come back to more about errors and so-called uncertainty management. So there will be more about this later on. But the second part here is about so-called two-port measurement techniques. So we talked about measuring the reflection coefficient and the impedance. So that is sort of looking into a system of some kind from a duct. But you could also, very often we are interested in what's, for instance, a muffler or a liner or some other system. So we would have an input, we have an output, and we want to know things like how much sound is reflected, transmitted, and absorbed within this system. So then we will have ducts on both sides of this test object, still with plane waves, And then we want to do wave decomposition using the 2 microphone method in both the ducts on both sides. So we can get the, as mentioned before, the P plus and P minus, or from them we can also calculate the pressure and the velocity. And in this case, I think the Q here is intended to be the flow velocity, or including the also Mach number information. But okay, P and Q, pressure and velocity, or rather the Q is, what's it called? It's multiplied by the cross-sectional area, so it's the but we can think about it as the velocity. And sometimes this is called the 4-pole technique. So there will be the pressure and velocity on each side, and they are related by 4 components of a matrix. So the pressure on the A side is determined by the pressure and flow velocity, or velocity at on the B side. And the velocity on the A side is determined also by some other 4-pole components multiplied by the pressure and velocity on the B side. So this is one possible way of expressing it. And then we also have the so-called scattering matrix, which is the thing that we usually use these days. So then we instead have the amplitudes of the waves on the A and B side. So in this case, the P minus are the incident waves, the waves going into the it seems, and the P plus is the ones going out. At least it looks like this from the figure on the top. Anyway, the waves going into, the amplitudes of the waves going into the 2-port, and the amplitudes of the waves going out from the 2-port, they are related by a matrix called the scattering matrix. So the terms of the scattering matrix can be, some of them can be interpreted as the reflection coefficients, and some others as the transmission coefficients. So these diagonal ones, 1, 1, and 2, 2, they are basically the reflection coefficients. And the other 2 are transmission coefficients. So in order to do this, we need to do wave decomposition on both sides of the sample. So the system can look like this. So we would have a flow duct, we'd have loudspeakers, we'd have a number of microphones on each side. We have a test object, and then we have a data acquisition system, signal conditioning, and so on. And then there are 2 possible ways. So it's the so-called 2-source technique. So in the 2-source technique, you get sufficient information by first running the loudspeakers on one side, and then you do the measurements, wave decomposition on both sides, and then you do run the loudspeakers on the other side and do the same. And in this way, you get sufficient information to solve, for instance, for the scattering matrix. Because you see here that we have 4 unknowns, so we need 4 equations to solve for them. So if we measure on both sides, we have used at least 4 microphones, so that gives us our 4 equations. But we also need to have 2 independent states to solve for this. That means that we need to run with the loudspeakers on both sides. So this is one option, the so-called two-source technique. The other option is the so-called two-load technique. So then we don't have loudspeakers on the downstream side. Instead, we change the duct system on the downstream side to get two different states or more independent equations. But we almost exclusively nowadays use the two-source method and not the two-load method, because this technique has lots of advantages. As long as you have sufficient equipment to set this up, you don't have to do a lot of changes to the setup. And if you change the downstream duct system, that could also change other things such as the flow speed or other things. So it's to be recommended to use the two source technique. So then it looks something like this in the minimum case, and then you can solve for the pressure and velocity or the amplitudes of the incoming and reflected waves, and then get the scattering matrix. By a matrix operation, which has to be done on a frequency by frequency basis. So a typical setup in our lab could look something like this. So we have a number of loudspeakers. Sometimes it could be less than 6 to 8, but okay. You can use more loudspeakers to increase the level that you excite with, because when you have flow speed which is a bit higher, you need to have a sufficiently high level of excitation in order to be able to get good results out of your acoustic measurements. And then 6 to 12 quarter-inch microphones, at least 6, I would say, 3 on each side, is common. And then flow speed measurements using PTO tube, measurements made before and after the acoustic measurements. Temperature monitoring is also good to include. As I mentioned before, that one issue in the measurements is these turbulent fluctuations that you can get, and you need to get rid of them and get the acoustic pressures. So to start with, you need to have an initial good signal to noise ratio by increasing the level of the input signals, and as I mentioned, multiple loudspeakers, using loudspeakers that can produce high levels. And then you can concentrate the signal energy to narrow frequency bands, because you have to think about what kind of excitation signal you use. You could have a broadband random signal, but very often these days we are using pure tone signals, and of course then you only get one frequency, so you have to move this frequency around and use so-called stepped sign measurements. However, in the task that you will work on later today, you will have a broadband random signal. But this will be a case without flow also, so it will be less complicated. Another flow noise suppression techniques is to use a reference signal to try to dig out the acoustic signal from the background noise. And you can pick a reference signal coming out of your measurement system, exciting the loudspeaker. You can pick it after amplification, or you could possibly also have a microphone signal as the reference, but okay, then all the microphones will be affected by the turbulence. So that's not that common to use this. Well, you could also put some kind of transducer in the loudspeaker, for instance, to get the reference. But in our case, we very often use, for instance, this signal. Well, it shouldn't be written like this. It should actually be the signal going into the loudspeaker that we would use. Yeah, this one. The one coming from the system going into the loudspeaker. Because one risk here is when you push your system, you try to excite the loudspeakers with a high level, that you could also create some kind of non-linear effects in between your reference and your output from the loudspeakers. And that's of course not good, because what we do is a linear system analysis. And then you can, when you have this reference, you can try to do different signal enhancement techniques. You can do frequency domain averaging using Welsh technique, which will reduce some of the stochastic fluctuations. And you will need to do this in the task you will work on later today. When you have this reference, you can do so-called synchronized time domain averaging, especially if you have periodic deterministic signals. And similar to this is so-called cross-spectrum based frequency domain averaging using the noise-free reference. And this number 3 is the one that we usually use when we have flow. This equation here shows how you could in principle get the outer spectrum of your pressure measurements by taking the cross spectrum between the reference and the microphone, which is denoted GRX. And if you don't know this outer spectrum or power spectrum and cross spectrum, I will talk a bit about this in my next talk about the introduction to your data analysis task. But basically, in theory, these cross spectra can be made very noise-free by using the reference. And then you use the power spectrum of the reference signal, which should be noise-free. So then you get an estimate of this, basically the pressure at the microphone, which is contaminated by the background noise, but you try to get a more noise-free estimate by doing this. And then typically you do some averaging. So you do more than you need to get one spectrum, and then you sum the estimates and you divide by the number of estimates that you have. Yeah, so I will soon come to the end here, but I will show a few examples of results that you can obtain. So this is just an example that we did on measuring on mufflers to illustrate also these signal enhancement techniques. So in this figure, you see frequency on the x-axis, you have transmission loss in dB. So this is based on the transmission coefficients from the scattering matrix. And then there's random excitation, and then there was 10,000 averages done using so-called Welsh technique averaging. So 10,000 averages is a lot. It took a long time to do it. And then there was some deterministic excitation with sawtooth excitation, also with 10,000 averages. with time domain, synchronized time domain averaging, and then there was the step sign excitation, 400 averages at each frequency, but then it took time to step to each frequency. All of these took more or less the same time to do and provided, in the end, very similar results, as you can see. So this is an illustration of how you can achieve a good result using these different types of averaging for enhancement of the signal. And then I want to just show an example of a more recent study that we did just 1 or 2 years ago. So we had the liner. Liner would be sort of a sound reducing device that you would typically use in aircraft engines, sitting on the side of a duct. And typically it would consist of, or in the most simple case, of a perforated plate with a backing cavity. So in this case it was 3D printed. You see the printed perforate in the photo, and then the cavities behind. This gives some of the geometry and so on. And then there was an experimental setup, so there were microphones here and here. There were also microphones in the line section, because there are other techniques to try to get the properties of this using these, but we will not talk about this here. Yeah, then there's specifications here about where the microphones were located. And then we obtained the scattering matrix using this two-source measurement technique. And based on this, you can calculate the transmission loss, which is basically 10 log times the transmission coefficient, which is these off-diagonal terms of the scattering matrix. And since we do with the excitation both from the upstream and downstream sides, you can get an estimate using this one or that one. So you get sort of an upstream and downstream estimate. And then you have also reflection coefficients, which are based on these scattering matrix terms, also compensated for the effect of flow. And then you can take also take the squared amplitude of these coefficients and get the transmission factor, and you can calculate the absorption, which is called large A, an absorption factor. So I will just show some examples of the results that you could get using this. So this is the transmission loss. It says uniform liner. We did measurements for different liners, but I will just show results for one case. So we have the two estimates, the downstream and upstream estimates of the transmission loss in the black and red curves. You can see that in a certain frequency range, around 1000 to 2000 hertz, it was very large. And for zero flow, there's no difference except for measurement error, probably between the two. One comment is that it actually starts to become very difficult to do measurements when you have 50 dB reduction, because you send in some from one side and almost nothing comes out on the other side. So the error increases in the downstream measurements. But anyway, when we add flow, we start to see a difference between the upstream and downstream here, which was one thing that we were interested in. And increasing the flow speed even more, we see that this is even more pronounced. So it's a larger difference between the two. And then one can look at also at reflection, transmission, and absorption. So in this case, the black is absorption, the red is reflection, the blue is transmission. And also then it's difference. The stars is the downstream estimate, the diamonds the upstream estimate. So again, we see that you more or less get the same without flow, and also we get very little transmission in this frequency range. You can also see that low transmission can depend either on absorption or in fact on reflection. So either nothing comes out on the other side because it's absorbed by the sound reducing device, or because it's reflected back. So it's of course interesting to find out how much is absorbed and how much is reflected. And you see that this now changes also when we start to have flow, and it also becomes difference in the two directions. So here it's quite clear. So one of them, the one with the stars, the downstream, that's much more is absorbed, and the diamonds, the upstream, reflection is still of importance in a certain frequency range. Yeah, I believe that could be my last slide. Yeah, just a summary. So what we talked about was a short introduction to the plane wave duct propagation, and then 2 microphone wave decompositions, sources of errors, how to determine impedance and reflection coefficient, 1 ports, and how to determine the passive 2 ports, scattering matrix, 4 poles, then something about flow, how to get rid of flow noise, the use of overdetermination, and a few application examples. Okay, so that was it. So